All right, for this one, we are going to be taking a look at this concept of solving multi-angle trig equations. This is just to help set up what we're going to be doing in the next lesson on polar graphs, where we kind of need to be able to handle some scenarios like this. So let me start running through some of these. Here's something we did first semester was solve an equation like this by replacing the sine of 2 theta with its double angle formula. So what we could do to solve this is I can replace the sine of 2 theta with 2 sine cosine, and then I'll bring down the rest of it, minus sine theta equals 0. And we would solve from there by factoring out sine theta as a common factor. That leaves me with 2 cosine theta minus 1. So it looks like this, and now that we factored it, we could set each factor equal to 0 and solve them separately. So we could say the sine of theta equals 0. We can say 2 cosine theta minus 1 equals 0. And then we'll just solve them separately. So the sine of what angle is 0? Well, if you just think of our basic unit circle here, where our sine value is 0, it would be at 0, and then pi, and then 2 pi, and then 3 pi, and then 4 pi, on and on and on. In other words, it's occurring every pi. So generally, we can just say it's n pi. Notice there's no domain restriction on this, so we're seeing these as they go on forever. If you get something like this, that's different, right? Because now it limits my answer to what it would be. And so if it was a case like this, this would just be 0 and pi and 2 pi if there's an equal sign. But anyway, you get the idea. So that would take care of the answers for him. As far as this one goes, add the 1, divide by 2. So we're saying the cosine of some angle is 1/2. So again, think of your unit circle at pi over 3 and 5 pi over 3. So pi over 3 and 5 pi over 3. And if there's no domain restriction, we're just going to slap on the plus 2n pi so that it can go on forever and ever and ever. Okay, so here's the issue though. That's a great way to solve, if possible. When I look at this one, if I replace this with 2 sine cosine equals 1, can I solve that? So if I were to say, if I were to say 2 sine theta cosine theta equals 1, I don't really have a way of solving that. I can't factor it the way that I did the one up above. I need another method for solving this. And so that's what we're going to work on today. So what do we do? In this case, if we just turn this into an inverse function. So if we said the inverse sine of 1 equals 2 theta. So the inverse sine of 1 equals 2 theta. So in general, what's the inverse sine of 1? What is, ignore this side for a minute. So the sine of what angle is 1? So we know that occurs at pi over 2. So this is pi over 2. And that would occur again every 2 pi, so we'd say plus 2n pi. But notice in this case, that wasn't solving for theta, that was solving for 2 theta. So I still need to divide everything by 2 in order to isolate my angle. So if I divide everything by 2, this becomes pi over 4. And this just becomes n pi. So now I have this. So for this one, now we're just going to take a look and say, okay, what are all the angles that fit that description, right? In other words, if I start plugging in 0 and 1 and 2 and 3 and 4, if I start plugging in numbers for n, what angles am I getting for that? If I have a restricted domain for this, right, this is kind of the forever answer. But if I have a restricted domain, let's find all of the answers to this just within that domain. So let's just start with 0. So if I plugged in a 0 for n, Well, what does that give you? So if we plugged in a 0 for n, that would just be pi over 4. If I plugged in a 1 for n, so pi over 4 plus pi would be 5 pi over 4. If I plug in a 2 for n, pi over 4 plus 2 pi, that's too big, right? I can't go outside of this. So if as soon as it gets bigger than 2 pi, I got to stop. So these are the two solutions that I would keep, are those guys right there. Okay, let me go down to this one. Again, similar thing, especially if I'm getting something like this. I don't even know a triple angle formula that I'd be plugging into that. I definitely don't want to solve it that way. So let's take the approach that we did on the previous one. So let's say the inverse sine, or the sine of what angle, is 1. So again, we know the sine of pi over 2 is 1. So just thinking of it in terms of an inverse function, we're saying the sine of what angle is 1. And I'm going to put the 3 theta on the other side. That's what we're solving for. So again, we knew this is pi over 2 plus 2n pi. So it looks like this. So now we got to take the extra steps. We got to divide everything by 3. So pi over 6 plus 2/3 n pi is theta. If there was no restriction on the domain, I would just leave it like that. But if there is a domain restriction like this, well, let's find all the answers from 0 to 2 pi. So if I plugged in a 0, well, if that becomes 0, then I just have pi over 6. If I plug in a 1, so 1/6 plus 2/3, so let's think of that as 1/6 plus 4/6, so 5/6. If I plug in a 2, all right, we got to get some good math going here. So if I plug in a 2, so that's going to be 4/3. So 4/3 plus a 6. So 8/6 plus 1/6 is 9/6, which would be 3 over 2. And that's still within my domain, so I'm good. I get to keep all 3 of these so far. If I plug in a 3, well, if I plug in a 3, those cancel. It would just be 2 pi. So a 1/6 plus 2 pi is bigger than 2 pi. I can't keep it, so he's out. I'm done. So those would be my 3 solutions that I would keep. All right, let me flip over to the back side. There's 2 more on here. I wanted to show you just a little variation on these. So for these last 2, what if I had a case like this? Well, I would have to start by dividing both sides by 3 before I do my inverse scenario. So the cosine of 2 theta is -1. So we're back to saying, okay, well, the cosine of what angle is -1? So the inverse cosine of -1 is our 2 theta. So where do we get cosine values that are -1? So that would be at pi plus 2 pi n, or 2n pi, either way, doesn't matter. So we get this. Well, keep going. We have to divide everything by 2. So pi over 2 plus, this would just become n pi. So there's our infinite solution set. If we have a restricted domain like this, we got to start coming up with those specific values. So let's start with 0. So pi over 2 plus 0. Plug in a 1. So pi over 2 plus pi. Plug in a 2. Pi over 2 plus 2 pi. That's too big. It's more than 2 pi. He's out. Obviously, things change if that changes, but that's the way we're looking at it for now. So we're just keeping those 2 answers because those are the only 2 within the solution set, within our domain. All right, last one. So I threw in a half angle on this. So we do have half angle formulas, but I wanted you to see this just in light of this process that I'm showing you right now. So again, let's isolate this guy. So we need to know the cosine of some angle is going to give us radical 2 over 2. So right now that angle is represented by theta over 2. So there's our setup. Well, so the cosine of what angle is radical 2 over 2? So we would get that at pi over 4 and 7 pi over 4. So I'm going to say it would occur at pi over 4 plus 2n pi and 7 pi over 4 plus 2n pi. So again, those are basically our infinite solution sets, but we have a restricted domain. Oh, I'm sorry, I got to finish this guy off. So those were equal to theta over 2. So to get theta by itself, let's multiply the 2 over to that side. So if I multiply this by 2, it becomes pi over 2 plus 4n pi. So that's his infinite solution set, and then we got one for this guy as well. So if I multiply the 2 over, this becomes 7 pi over 2 plus 4n pi. So we're going to run out of answers real quick on this one. So if I plugged in a 0 for my n here, I'm just going to have pi over 2. If I did plug in a 1, this is 4 pi, so I'm way bigger than 2 pi at that point. So I can't even go any further. On this one, if I plugged in a 0, I get 7 pi over 2. Again, if I try to plug in a 1 or anything higher, I'm way bigger than 2 pi at that point, so I can't use those within this domain. And so those would be the only two answers I'd be allowed to keep. So that's it for this one.